Most developers think they are using cloud correctly because their application is running and their users are not complaining. That is not the same thing as using cloud correctly. That is just using cloud. The gap between those two things is where companies hemorrhage money, where systems fail, GAT, the worst possible moment, where security breaches happen that should have been impossible, and where engineering teams spend their careers fighting fires that needed to start. The mistakes are not obvious. They are not the kind of thing that shows up immediately in your logs or you monitoring dashboard. They compound quietly over months and years until the bill is 3 times what it should be, the architecture is too tangled to refactor cleanly, and the team has normalized a level of operational pain that they have forgotten is not inevitable. Here is what 99% of developers are doing wrong in the cloud and exactly how to fix each one. The first mistake is treating cloud like it is just someone else's server. This is the foundational error that everything else flows from. When organizations first migrate to cloud, they take their existing on-premises architecture, lift it, and drop it into virtual machines running on AWS or Azure or Google Cloud. Same structure, same assumptions, same patterns, just hosted somewhere else. They pay cloud prices for on-premises thinking and get the worst of both worlds. The entire value proposition of cloud computing is that resources are elastic, that you pay for what you use, that you can scale horizontally instead of vertically, and that managed services can replace enormous amounts of operational overhead that your team should not be carrying. None of that value is accessible if you are running a fleet of always-on virtual machines sized for peak load that sit at 15% utilization 80% of the time. The fix is to audit every resource you are running right now and ask honestly whether it needs to exist as a persistent always-on server, or whether it could be replaced with a managed service, a serverless function, a container that spins up on demand, or an auto-scaling group that shrinks to 0 during off-peak hours. Start with your workloads that have variable traffic patterns. A service that handles 10 requests per minute at 3 in the morning and 10,000 requests per minute at noon should not be provisioned for the noon load around the clock. That is money leaving your account every hour for capacity that is sitting completely idle and that your users are not benefiting from. The second mistake is ignoring the principle of least privilege until something goes wrong. Walk through the IAM configuration of almost any production cloud environment that was built under deadline pressure and you will find the same things. Service accounts with administrator access, because it was easier than figuring out the exact permissions needed. EC2 instances with roles that can read and write to every S3 bucket. In the they should never touch, because the developer copied a policy from Stack Overflow without reading it carefully. Developer accounts with console access that has not been reviewed or rotated in 18 months. These are not theoretical risks. They are the specific conditions that turn a compromised credential or a misconfigured application into a catastrophic breach. The principle of least privilege means every identity, every service account, every role, every user gets exactly the permissions it needs to do its job and nothing more. Implementing it properly requires going through your IAM policies and asking for every permission granted what specific action by what specific resource requires this. If you cannot answer that question specifically, the permission should not exist. On AWS, use IAM, Access Analyzer, to identify policies that grant access to resources outside your account or that grant permissions that are not being used. AWS tracks which permissions are actually exercised and can show you permissions that have been granted but never used in the past 90 days. Those unused permissions are the attack surface you are maintaining for no operational benefit. Remove them. On Azure and GCP, the equivalent tooling exists under different names, but the discipline is identical. Scope everything down. Review it quarterly. Treat overly permissive IAM as a bug, not a convenience. The third mistake is building without thinking about failure domains. Most developers design for the happy path. The database is up, the network is available, the downstream service responds within its SLA, the deployment goes smoothly. Cloud infrastructure is reliable enough that this assumption holds most of the time, which is exactly what makes it dangerous. Most of the time is not all of the time. And in distributed systems, the failure modes that matter are not the obvious ones where a whole region goes down and your monitoring screams. They are the subtle ones. The database connection pool that exhausts silently under load. The third-party API that starts returning 500 errors intermittently. The deployment that works in every environment except production because of a configuration difference nobody documented. The cache that fills up and starts evicting entries in a way that sends stampeding requests directly to the database. Building for failure means every service you write assumes that every dependency it calls can fail at any moment and handles that failure gracefully. It means implementing circuit breakers so that a failing downstream service does not cascade failures upstream. It means setting timeouts on every network call, because a hanging call that never returns is worse than a fast failure. It means designing your data layer so that a single database instance going away does not take your entire application offline. It means testing failure scenarios deliberately and regularly, not waiting to discover them in production at 2 in the morning during peak traffic. Chaos engineering, the practice of deliberately introducing failures into your system to verify that it handles them correctly, is not an advanced practice reserved for companies at Google's scale. It is a basic discipline that any team running production workloads in cloud should be practicing at whatever scale makes sense for their system. The fourth mistake is ignoring cloud costs until the bill arrives. Cloud billing is intentionally complex. The pricing models for compute, storage, data transfer, API calls, managed services, support tiers, and reserve capacity involve enough variables that even experienced cloud architects find it genuinely difficult to predict what a system will cost under real production load. Most teams solve this problem by not looking at the bill until it arrives, and then experiencing sticker shock and scrambling to find the biggest line items to cut. This is the most expensive possible approach to cloud cost management because the waste has been accumulating for months before anyone noticed it. The correct approach is to treat cloud cost as an engineering metric that is reviewed with the same regularity and seriousness as latency, error rate, and availability. Set up billing alerts that notify your team when spending crosses defined thresholds so that cost anomalies are caught in hours, not months. Use cost allocation tags on every resource so that spending can be attributed to specific teams, services, and features. When you cannot see which part of your system is driving cost, you cannot make intelligent decisions about where to optimize. On AWS, use Cost Explorer and set up cost anomaly detection. On Azure, use cost management and budgets. On GCP, use the billing reports and budget alerts built into the console. The tooling exists on every major platform. Using it consistently is a disciplined decision, not a technical one. The fifth mistake is not understanding data transfer costs. This is the single most common source of cloud bill shock, and it catches developers off guard because it is almost entirely invisible during development and testing. Every major cloud provider charges for data leaving their network, outbound data transfer to the internet, data moving between availability zones within the same region, data moving between regions, data moving from one cloud service to another cloud service when that traffic crosses a billing boundary. These charges accumulate silently and they scale directly with your traffic. A system that transfers a terabyte of data per day at cloud data transfer rates is paying a significant amount every month for something that most developers never explicitly designed or accounted for. The fix starts with understanding your data flow. Draw out every path that data takes through your system and identify which of those paths cross billing boundaries. Data moving between services in the same availability zone is typically free or very cheap. Data moving between availability zones in the same region costs more. Data moving between regions costs more still. Data leaving to the internet costs the most. Once you understand the flow, you can make architectural decisions that minimize expensive transfers. Placing services that communicate heavily in the same availability tie zone. Using content delivery networks to serve static assets from edge locations instead of transferring them from your origin servers for every request. Compressing data before transmission to reduce the volume E being transferred. Caching aggressively at the right layers so that the same data is not fetched and transferred repeatedly. The sixth mistake is manual deployments and undocumented infrastructure. If your team can make changes to production infrastructure by clicking around in the CA, reproducible, not auditable, and not recoverable in a predictable time frame if something goes wrong. Manual changes made through the console leave no record of who made the change, what the previous state was, or why the change was made. When something breaks after a manual change, the debugging process starts with archaeology, instead of starting with a clear record of what changed and when. When you need to recreate an environment, whether for disaster recovery, for spinning up a staging environment that matches production, or for expanding to a new region, you are doing it from memory and tribal knowledge instead of from code. Infrastructure as code is not an advanced practice. It is the baseline. Every resource in your cloud environment should be defined in code using Terraform, AWS CloudFormation, AWS CDK, Pulumi, or whatever to. L fits your team's workflow and existing expertise. That code should live in version control alongside your application code. Changes to infrastructure should go through the same review process as changes to application code, a pull request, a review, an approval, a merge. The Cloud Console should be used for observation and monitoring, not for making changes. Treat a manual console change to a production resource the same way you would treat a manual change to production application code, as a process failure that needs to be corrected and prevented. The seventh mistake is neglecting observability until something is broken. Most teams set up basic monitoring when they first deploy a service. CPU utilization, memory usage, basic uptime checks. And then they stop because the service is running and there are features to build. The problem is that basic infrastructure metrics tell you very little about whether your application is actually working correctly for users. A service can have normal CPU and memory and still be returning errors on 30% of requests. It can be up from a ping perspective and be completely broken for users in a specific geographic region. It can be handling requests and returning 200 status codes while silently corrupting data in edge cases that nobody has written an alert for. Real observability means three things working together: metrics that tell you what your system is doing in aggregate, request rates, error rates, latency percentiles, not just infrastructure level numbers. Logs that tell you what happened for specific requests with enough context to diagnose PR problems without needing to reproduce them. Distributed traces that show you how a single request traveled through every service in your system and where time was spent. Without all three of these in place, you are operating blind. You're finding out that something is wrong when users complain, or when an alert fires on a metric that is already at a crisis level, rather than catching the early signals that something is degrading before it becomes a full outage. Instrument your applications with structured logging from the beginning. Use a logging format that machines can parse, not just humans, so that you can query and aggregate logs at scale. Implement distributed tracing using OpenTelemetry, which is the open standard that works across every major cloud provider and most major frameworks. Define your service level objectives before you deploy, not after something breaks. An SLO is a statement of what good looks like for your users. 99.9% of requests complete in under 200 milliseconds. Error rate stays below 0.1% over any rolling 7-day window. When you have defined what good looks like, you can build alerts that fire when you are trending toward bad, rather than alerts that fire when you have already arrived there. The eighth mistake is treating security as something you add later. Security in cloud is not a feature you bolt on after the application is working. It is a set of decisions made at every layer of the architecture from the beginning that become progressively more expensive and disruptive to retrofit as the system grows. Unencrypted data at rest, because encryption was not enabled when the database was provisioned and nobody went back to turn it on. Public S3 buckets that were made public for a quick test and never locked down. Security groups that allow inbound traffic from 0.0.0.0/0 because it was the fastest way to get something working, and the ticket to restrict it was never created. Secrets stored in environment variables or worse in source code because the team had not set up a secrets manager yet. Enable encryption at rest on every data store you provision. It is a checkbox during creation on every major cloud provider, and there is no performance justification for skipping it on anything that holds real data. Use your cloud provider secrets management service, AWS, Secrets Manager, Azure, Key Vault, GCP Secret Manager. For every credential, API key, database password, and certificate your application uses. Never put secrets in environment variables that are visible in your deployment configuration or in source code that lives in version control. Audit your network security groups and firewall rules quarterly, and remove any rule that cannot be justified by a specific current requirement. Enable CloudTrail or the equivalent audit logging on your account so that every API call made against your infrastructure is logged, and that log cannot be tampered with by whoever made the call. The developers who use cloud correctly are not the ones with the most sophisticated architectures or the largest teams. They are the ones who treat cloud as a discipline that requires the same rigor, the same review cycles, and the same commitment to continuous improvement that they apply to their application code. The bill rewards that discipline. The incident log rewards it. The 3 in the morning pager rewards it. Start with one mistake from this list. Fix it completely. Then move to the next one. The gap between how most teams use cloud and how cloud should be used is not closed in a single sprint, but every step toward closing it is a step away from the class of problems that are entirely self-inflicted and entirely preventable.